In chapter 10, specifically 10.2, I believe, our book talks about statistics and measures of center and measures of spread. Our measures of center are more familiar to us: mean, median, mode, mid-range. And then we have two measures of spread that we use. We focus on both range and standard deviation. Now, before we talk about how to calculate standard deviation, because that's the long part, we're going to talk about our normal distribution curve. We have two basic ways to graph, to show visually how our data is dispersed or spread out. The first way is with a box and whisker plot, which you evaluated and you worked through setting up with some practice activities that we did and activity manual activities. The box and whisker plot is centered on the median. So we look at that physical center of the data when it's organized from least to greatest, and we take that and we literally divide our data into fourths. And so we see how spread out it is based on how spread out those quarter values are. We've got our median in the center. We've got 25% above and below the median in the box. So there's a total of 50% of our data roughly. And then we have the other 50% spread out in the upper and lower whiskers. So the box and whisker plot is centered on the median, and it talks about the spread of the data based on that median. Our other way to look at the dispersion or the spread of the data is using standard deviation. Now, standard deviation is looking at the average deviation or the average distance from center. When we use standard deviation, instead of looking at the median as our measure of center, we're focusing on the mean, on X bar, or what we usually refer to as the average as our measure of center. Another thing that is another thing that is focused on the mean and the standard deviation is when we have our curve. Now, the curve can be skewed left or right, but we hear it referenced to when we have a normal distribution. We talk about the bell curve. We used to. We talk about any data set that is normally distributed as being on this normal distribution curve. Now, our normal distribution curve is centered on the mean, and we are looking at how many standard deviations away from the mean our data falls. So our mean, our normal distribution curve, is centered on the mean. That X bar is going to be right in the middle of our normal distribution curve. If our data set is normally distributed, our curve looks like this. It's balanced around the mean. And typically we see that we have our highest concentration of data points at the mean. There are a lot of population data sets that are normally distributed. Height, weight, it's been a long morning already, so I'm not even going to try to list anymore. But you see a lot of population data that follows a normal distribution, centered on the mean. And then we can talk about what percentage of the data falls within so many standard deviations of the mean. When I do box and whisker plot, I'm talking about the median, and then I've got quartiles. I've got my first quartile, second quartile, third quartile, and fourth quartile, which correspond to the first quarter of the data, the second quarter of the data, the third quarter of the data, and the fourth quarter of the data. Again, roughly, I've got 50% of my data right here in the box, and the other 50% is evenly distributed amongst the whiskers. The length of the whisker shows how spread out it is. My curve can be skewed. If it's not a normal distribution, it might peak over here and be skewed to the right, or it might start with a tail and peak over here. We call that left skewed. This is what my normal distribution curve looks like. When my data set is normally distributed, and I'm sorry it's taken me this long to get there, but when my data set is normally distributed, I see that I have about 68% of my data, 68% of my data within one standard deviation of the mean. So x bar minus 1 standard deviation is 1 standard deviation below the mean. X bar plus 1 standard deviation is 1 standard deviation above the mean. Now, what does that look like as far as example with values? Let's say that for whatever my data set is, the mean is 50. And the standard deviation, the average variance from the mean, the average distance from the mean is 5. That means that, let's say this is a test score. The average grade is 50, and 68% of the people who take the test are going to score between 45 and 55, because that would be 1 standard deviation below the mean and 1 standard deviation above the mean. So if my mean is 50, this would be 45 and 55. 68% of the people that take the test are going to be within 1 standard deviation of the mean. If I move out another standard deviation, so let's say I move out here, so that I've gone 2 standard deviations from the mean. Well, once I've moved out 2 standard deviations of the mean, I have included 95% of the data. So this is going to be x bar minus 2s and x bar plus 2s. Well, what values does that represent for our example? If our mean is 50 and I go back 2 standard deviations, I'm at 40. And if our mean is 50 and I go forward 2 standard deviations, I'm at 60. So that means that if this is a test, 95% of the people taking the test can be expected to score between 40 and 60 on this particular test. Let's go a third standard deviation. Now, if I go a third standard deviation, and I never stack this quite where I can write everything I need to write. If I go a third standard deviation, though, I have moved out to include 99.7% of the data. So within 3 standard deviations of the mean, I am including 99.7% of the data. What scores, for our example, what scores would those be? Well, 1 standard deviation is 5, 3 standard deviations would be 15 points below the mean. So that would be at 35, and this would be 15 points above the mean at 65. That means almost everyone, 99.7% of the people who take this test are going to score between a 35 and 65. Okay, so what's left? Well, what is left are the percentages that are in these tails over here, above and below. This tail at the lower end, this tail at the upper end, beyond 3 standard deviations from the mean, I've got the remaining 0.3% of the data. Well, that 0.3% is spaced evenly above and below. So 0.15% of the data is in this lower tail, and 0.15% of the data, the population, is in this upper tail. To put this into a little bit of perspective, my daughter has bone density issues, and she's really got some soft bones. When we did a bone density scan, they came back with a Z-score of a -4 something, which means that her bone density is more than 4 standard deviations below the norm for her age, which means she is well over here in this tail end percentile. If you're going to get some questions about the standard deviation, the normal curve, distribution curve, what would you say would be the percentage of scores that are more than 2 standard deviations above the mean? What percentage of scores would fall more than 2 standard deviations above the mean? Well, at 2 standard deviations, I've got 95% of my data accounted for, which leaves 5% of the data beyond 2 standard deviations. But that beyond 2 standard deviations is split between above and below. So half of that remaining 5% is below 2 standard deviations below the mean. Half of that 5% is 2 standard deviations above the mean. So What percent is more of the data is more than 2 standard deviations above the mean? Just 2.5% of the data falls there. Now let's look at how we calculate the standard deviation. Now, I have this nice chart available to you. There's a blank one on the back. We're just going to do this front one, this first example. The back one that is blank, you have to set up to use for an example problem, whatever you want to do with that. I just wanted to get one good example in your notes because standard deviation tends to be a bit of a challenge for some students. I apologize for the beeping in the other room. My daughter's having oxygen trouble today. Okay. So standard deviation is a measure of dispersion or spread. It's used to tell how far on average any data point is from the mean. The smaller the standard deviation, the closer those scores are on average to the mean. And the larger the standard deviation, the more widely spread out the scores are on average from the mean. So standard deviation is an average. There are different ways to, they're all basically the same, but there are different ways to calculate standard deviation depending on what branch of statistics you're in and on whether you're looking at population or sample data. We are keeping it very, very basic. We are going to calculate standard deviation one way, and we are going to assume we have population data. Now, I'm going to tell you what that means when we get to the point where that matters, but know that we are calculating the average distance from the mean. And to find the standard deviation, we need to know what the mean is, and we need to think about how many data points we have. So for this problem, we have test scores for a class. It's all of the test scores in the class, so it is population data. If we find the mean, we add the scores up and divide by how many scores there are. In this case, we have 10 scores, and we discover that the mean is 66. So X bar is 66. Now, to calculate the average distance from the mean, or the standard deviation, I'm going to do some stuff to keep myself organized. So I want you to list the 10 test scores in order from least to greatest, just because it helps a lot of us, including me, again, to keep things organized. So that's the first thing you do. Go through these 10 scores, list them from least to greatest. All right, if you're not done with that, I want you to pause the video until you're caught up. If you are done, go ahead and do me a favor and tell me what is the sum of these scores. Now this is sigma. This symbol is sigma, and it literally means sum. If I add up all my scores, and you had to add up all your scores to find X bar, to find the mean. If I add up all those scores, I get a sum of 660. So you're familiar with this symbol sigma. When we get over here and we see it again in a more complex equation, it's not going to mess you up. Okay, the next step in calculating the standard deviation is to find the difference of the mean, difference from the mean of each score. Now notice that I'm starting with a score and subtracting the mean. That means that for my scores below the mean, I'm going to have a negative difference. And for my scores higher than the mean, I'm going to have a positive difference. So pause the video, calculate those differences from the mean. All right, make sure your differences from the mean match my differences from the mean, just so we can catch any mistakes that might have been made. And then I want you to add all of these differences. I want you to sum these differences. If you sum these differences, if you put them all into your calculator and add them up, you should get a sum of 0 here. Well, why did that happen? That happened because we started with center, and then we looked to see how far away from center each of our data points lies. This is a physical representation in the sense that it's a balance point. The mean is the balance point for our data set. If I had a scale and I could place things different distances, if I could place weights different distances from the mean, the sum of my weights are going to sum to 0 so that my scale is in balance and it stays flat. Since my sum is 0, that doesn't help me in calculating the standard deviation. I have to do something about the fact that those positives and negatives are going to add to 0. The way that we are going to choose to deal with that is by squaring each of those differences. When I square the differences, all the positive values stay positive. All the negative values become positive, because when I square that negative number, negative 44 times negative 44 is a positive 1,936. So I want you to do that. I want you to square all of these differences. All of these values are going to come out to be positive. Pause the video, find the squares, and then resume the video to move forward with us. Okay, check your squares against mine to make sure that you got the same values. And then we're going to find this sum. Right here, this is what we're finding for this box. We're going to sum the squares of our differences, and there should be a 2 there. We're going to sum the squares of our differences. So we're going to add together this column. When you plug this all into your calculator and add it together, and it's important that you're doing this on your calculator and not just following along, so that you start to notice what things you do wrong, to make sure that you know to correct them when you are doing it on your own. So now I have the sum of the squared differences. I'm going to take that sum, and because we have population data, we know everyone's test scores. We're going to divide the sum of the squared differences by n, by the number of data points in my population. Now, if I didn't have population data, if I just had a sample, well, we know that since not every score would be represented in our sample, we know that we're going to have some variation and we are not going to have an exact result. And to accommodate for that, if I were dealing with sample data, I would divide by n minus 1, by a smaller denominator, in order to give some allowances for differences between the sample data and what my population would actually be. But we're assuming in this class, every time you do standard deviation, we are assuming we have population data, so we're just going to divide by n. So you are going to take the sum of your squared deviations and divide it by n. And when we divide by 10, that's super easy. We are just moving that decimal point one place. And this is what we call the variance. So this is my variance for this data. It is the average of the squared deviations. The variance is the average of the squared deviations from the mean. Now, the average of the squared deviations, I still have that thing that I squared it, right? Well, I have to unsquare it in order to get the standard deviation. I've got the average of the squared deviations. To get the standard deviation, I have to unsquare that. So I'm going to take the square root of my variance. I'm going to take the square root of my variance. And for this data, I'm just going to round it to the nearest tenth. When I take the square root of my variance, I get a standard deviation of, and I'm going to change that equal sign to an approximately symbol, approximately 28.9. That is what my standard deviation is for this data set.